Hi kids, Miss Block here, and today, as part of the Age of the Earth unit, we are going to examine and review absolute age. As always, feel free to pause and rewind this video to review any concepts that you have trouble with or you might have missed the first time around. You should have your reference tables handy and your notes to help you out as we go through. Ready? Let's get started. So, in Earth science, we've been talking about how we date various objects on the Earth. And we talked about how early in our studies of Earth science, we would use the concept of relative age. And relative age is a comparison or a sequence of events where you look at how old a fossil or rock or event is compared or relative to the other items and fossils around it. Likewise, now, one of the newer techniques that have come about is using absolute age dating techniques. And here we're able to come up with a numerical age of a particular rock, fossil, or event. Comparing these two can be best looked at if we were to look at some children. So right here in the top picture is how you talk about maybe your place if you're one of multiple siblings. For example, these middle children, these intermediate children, they are older relative to the youngest child, but younger relative to the oldest child. So depending on where we place them, all right, they're older or younger. We also don't know how old or how young those children are. When we talk about absolute age, though, we can give actual numbers associated with it. And it's sometimes easier for people to figure out or have an understanding of how old something is when we have these numbers associated. In this video, we're actually going to examine absolute age and the techniques that we use to figure out how old exactly something is without just taking a guess or comparing it to other items. Now, we're going to talk about radioactive dating, but before we get there, we need to do a quick review of the atom. So right here, this should be something that you looked at in science last year. And right here, you can see a basic atom. Right here, the first subatomic particle that you probably looked at was the proton, found in the nucleus. It had a positive charge, and it gave the properties or characteristics of that atom. All right, so if that atom of a particular element would have certain characteristics. I changed the number of protons, I'm now changing the characteristics or what type of element it is. You also probably talked at length about electrons. They have a negative charge. They're found outside of the nucleus. If I change the number of electrons, I can end up sometimes having a negative overall charge to my atom or a positive overall charge to my atom. Electrons were also used in bonding to other atoms. Last but not least are the neutrons, and you probably talked about how neutrons were found in the nucleus just like the proton, and they were kind of massive, so they had contributed to that atomic weight. You also probably mentioned that neutrons had a neutral charge and left it at that. Well, we're going to talk at length right now about how neutrons were used with our radioactive dating, or if we had an uneven number of neutrons to protons, okay, you would end up with something called an isotope. And an isotope is a version of an element with the same number of protons but a different number of neutrons. Okay? So if we were to look right here, here's a sample of basic normal stable carbon. This carbon right here has an equal number of protons and an equal number of neutrons. 6 protons, 6 neutrons. Hence the name right here, C12 or carbon 12. Likewise, I can have right here an isotope of carbon. So this is carbon 14. I still have those 6 protons because it is carbon, but I have a different number of neutrons from protons. Okay, so 6 plus 8 gives me this 14 over here. 6 neutrons, 8 neutrons. So when I have that equal number of protons to neutrons, I end up with a stable atom. However, when it's an unequal number of neutrons to protons, it's unstable. Another term to describe an unstable atom is radioactive. And when something's radioactive, it wants to break down or decay. So isotopes will decay into a more stable form. Luckily for us, they'll decay at a predictable rate. And this allows us to date rocks, fossils, and geologic events because they're decay rate is so predictable and unchanging. We call this rate at which they decay a half-life because it's the amount of time it takes for half of that substance to decay. So it's the amount of time it takes for half of the radioactive isotopes present in that substance to break down or to become stable. Right here are 4 radioactive isotopes that we're going to look at in earth science. Okay, we have carbon-14, which breaks down into nitrogen-14, and it takes for this carbon-14 5,700 years to break down, to have half of the isotopes in that sample break down. We also have potassium-40. That will take 1.3 billion years for the isotopes in that sample, for half of them to break down. Uranium-238, it will take 4.5 billion years for half of the isotopes present in the sample to break down. And in rubidium-87, it takes 49 billion years for half of the isotopes present in that sample to break down. So you can see how long it takes for it to break down and decay. We will look for certain ones depending on what our needs are. So like for example, our carbon-14 here, we would use for something that we have an idea of being relatively young, or something that was recently alive, say like a woolly mammoth or a mastodon. All right? Likewise, we would use potassium-40 for really old rocks. It wouldn't have too much, or not enough would have broken down to use for something that was recently alive, since it takes 1.3 billion years for half of it to disintegrate. Uranium-238 has the same half-life, very similar to how old the Earth is. Okay? The Earth is inferred to be 4.6 billion years old. Uranium-238's half-life is 4.5 billion, so we'd use that for like formation of the solar system. Rubidium-87's half-life is greater than what we infer the existence of the universe to be. So that one has a super long half-life. That takes a long time to break down. And as I mentioned earlier, the decay rate is constant, meaning it never ever changes, and you can't do anything to actually change that decay rate. So if I were to heat it up, cool it down, crush it, the rate at which those isotopes break down will still stay the same. You cannot change the half-life length. Let's take a look at a sample and examine how exactly it would break down. So right here, we're going to pretend that this little grid right here represents a sample of carbon-14 that's breaking down into its more stable form or daughter product, nitrogen-14. Right now, we can see that none of it has broken down. Okay? And before we even think about how much would break down, we need to know how long it will take. So we're going to do a quick check on the reference tables. 5.7 times 10 to the third, which is 5,700 years old. So when I look here, none of it is broken down. No time has passed. 100% of it is radioactive or unstable, and 0% is stable. Let's say now some time passes, or maybe I find a different one, and 0 half-lives has gone through here. Let's say I find a different sample, and I find that 50% of it has been broken down, represented by this green shading right here. How old would this sample be if 50% is unstable and 50% is unstable? Well, it would be 5,700 years, because that's how much time it would take for half of it to break down. All right, so in 5,700 years, 50% would be unstable or radioactive, and 50% would be stable or decayed. So 50% decayed, 50% undecayed. This represents one half-life. Right here we can see that 25% is radioactive. Half of what was unstable has broken down. Okay, so half and half. We only break down what's radioactive, and we're not going to have the same amount every time, since the amount that's radioactive gets smaller and smaller each time I break it in half. So right now, I was able to have that, and I can see that 25% is unstable, while 75% is stable. That means that about 11,400 years have passed. How do I know? Because I've gone through 2 half-lives. Because 25% is unstable. So 5,700 times 2 tells me that it's going to be 11,400 years old. Now, let's say that I was decaying that radioactive portion right there, that 25%, I have that. How old would this be now? I would have 12.5% unstable, so it would be 17,100 years old. I can figure this out because I went through 3 half-lives. 3 times 5,700 tells me that it's 17,100 years old. We can also see right here, the more radioactive it is, the younger my sample will be. The less radioactive it is, the older it's going to be. So that can also give you an indication or a little helpful hint when trying to figure out how old something should be. I can also graph my results on a graph that shows how it would change. So if I look right here, we can see a basic graph created by the decaying and undecaying changing. Okay, this graph can also help me out if I'm trying to figure out the half-life of a sample. I can look and see when we're at 50% right here. I can also see when it's 50% decay product and radioactive material. It's when they intersect, or I can go over to the 50%. I follow it down to the bottom, and I can get a rough estimate of the half-life for that sample. We can also see as time increases, the percentage of material that has decayed will increase. However, as time increases, the radioactive material present will decrease. Okay? And we can just see that both on the chart. So if you have a chart where they're both going down or both going up, you probably might have read something wrong or something's incorrect with that. Now you might have noticed that these lines are not perfectly straight, and that's on purpose because the amount that we're having, it's not always going to be the same increment. You're not always going to decrease by 10 or decrease by 5. You're always going to be having it and having that percentage. Let me show you here. So right here I had the decay of carbon-14, and I keep having the amount that I have. So if I start off with 10 grams and I go through one half-life, it's going to go from 10 to 5. If I have 5, half of 5 is not 5, but 2.5. And then if I go through another half-life and I have 2.5, I end up with 1.25. So that amount having each time is why I'm going to have this curve to my graph. Also keep in mind, as our isotopes disintegrate, it's random throughout the sample. It's not just going to be one half radioactive, the other half, don't touch that one end. It's randomly scattered throughout the isotopes. So you can see with time, we end up having less and less of those parent isotopes, or what we started with, and more the daughter product, or what it's the stable version of that, or what it disintegrates into. Please keep in mind, since radioactive isotopes decay at different rates, we can use them to date different events and things, like I mentioned earlier. You want to use the appropriate radioactive isotope to date your item, so please use that chart and the information given on ESRT page 1 to help you figure out which one is best suited. You're not going to use carbon-14 to date the formation of the solar system, nor would you use rubidium-87 to maybe date early Neanderthal findings and whatnot. Okay, look at the half-life as an indicator. I hope you found this useful. Please again review it and rewatch it if you have anything that you're confused about or uncertain. I'll see you in Extra Help if you have any questions. Take care. Bye-bye.